I am Krishna Hanumantu from Chennai Mathematical Institute. I am going to teach a course on abstract group theory over the next 8 weeks. My goal here is to introduce the basic ideas, give some motivation and do some standard theorems in the subject, and to explain a little bit about why groups are very important in various areas of mathematics and even outside. So, today I want to start off by first giving you some examples which I hope will motivate the definition, and then I will give you the definition and look at some properties. Okay, so, the course is on introduction to abstract group theory. Okay. Groups are algebraic objects which abstract, as the word suggests, certain important features of well known mathematical objects. So, I want to do some examples which illustrate this, and in each example I want to point out the crucial piece of information that we want to retain. Okay. So, the first and most important example of a group that we all know is the group of integers. So, this Z is the symbol for this. So, this is the set. Let us start with this. It is the set of all integers. So, integers are, for example, these are all negative integers, 0 and positive integers. So, it is an infinite set consisting of these numbers. Okay. Groups are sets along with a certain operation on them. So, and the most familiar operation for us on Z is the addition. So, what is this? Addition. We all know how to add two integers. And what are the properties of addition? Let us try to identify these that we want to abstract out and define a group later. So, what is the property of addition? So, given any two integers, we can add them and we get another integer. So, if we add two integers, we get another integers. So, this is the starting point. So, we say that adding integers is a binary operation in the on the set of integers. So, I will define this in more formal setting later, but it simply means the word binary refers to the fact that we add two integers to get a third integer. So, for example, if you add 3 and 2, you get 5. If you add 5 and minus 2, we get 3. So, if you perform the operation of addition on two integers, we get another, the output is one integer. So, input is two integers, operation is addition, output is one integer. So, that is the first property of addition. So, let us look at another important property of addition. There is a special element called 0. 0 is a special element. So, what do I mean by that? So, let me say 0 is a special element in Z, which is to say special in the following sense. If I add, if n is any integer, so let us take an arbitrary element n, then if I do n plus 0, I get n back, which is also same as 0 plus n. 0 is the only integer with this property. If you add 0 to this n integer, you get that integer back. No other integer has this property. If you add 1 to an integer, you do not get the integer back. So, 0 is called the identity element. Identity element for addition. Okay. So, this is the second property. So, remember again, the first property was if you add two integers, you get another integer. You have a special element that we call identity element, which has the property that if you add this to any element, you get the element back, you do nothing, in other words. The third important property that I want to identify is every element, which in this case is an integer, has an inverse. What is an inverse? Inverse is an element that you can add to get the identity element. So, for example, if you, what element do we want to add to 5? So, we want to add something to 5 to get 0. What is that element? That element is obviously minus 5. If you want to add something to minus 3 to get 0, you will add 3. More generally, if you want to add minus n to n, you get 0. So, this is an inverse. So, inverse is the opposite. So, in some sense, if you add inverse to an element, you get the identity element, which I have already declared a special element, called it the identity element. So, every element has an inverse. So, we have identified 3 properties of addition on integers. If you add 2 integers, you get another integer. There is a special element called 0, and every element has an inverse. Finally, I want to note the following property of addition. So, remember, addition is a binary operation. So, in other words, we can add 2 elements. If you add 3 and 2, you get 5, but we cannot add a priori 3 elements. How do you add 3 elements? What is the meaning of this? Remember, addition is only a binary operation. Given 2 things, we produce 1 output. But if you are given 3 things, there are 2 possible ways of doing the addition. So, if I asked you what is 3 plus 2 plus 5, you would first, one option is to combine 3 and 2 first, and then this, now 3 plus 2 is again an integer, and add 5 to it. So, this is 3 plus 2 in bracket, that means you apply the binary operation to 3 and 2, and for which you get 5, and then you add 5. So, that gives you 10. But you can also do the following, you can first add 2 and 5. The point is to group 2 things together. In the first option, I grouped 3 and 2, in the second option, I will group 2 and 5. So, then I get 3 plus 7, which is also 10. So, I get the same answer. So, no matter how I group elements, I get the same answer, which is very important. Otherwise, there will be an ambiguity on how to add 3 elements or 4 elements or 5 elements. So, this is called associativity of addition. Associativity means we can group things, again I will do this more formally later, but we can group, given 3 elements, we can group 2 of them together in 2 different ways, and we get the same answer. Okay. So, this is the 4th property of addition on integers. So, we can unambiguously add 3 elements. So, we can use the associativity property of addition. So, just to recall properties of addition: on integers. 1, it is closed. So, I am going to use this word from now on, it is closed under addition. Which is, whenever we say a property is closed, that means if I apply that property, I am within the same set. So, if I take 2 integers, in other words 2 elements of Z, perform addition, I land again in Z. There is an identity, the second property is there is an identity element, namely 0. The 0 is an identity element. Every element has an inverse, namely minus n is the inverse of n. addition is associative is the last property. So, these are the 4 properties of addition on Z. If you think about it a little bit, there is another property of addition that I did not highlight now, but which we will come to later. So, I will record it here and we will come back to it later. Another property of addition is, for example, if I add 3 plus 6, I get 9, which is same as 6 plus 3. So, the order in which I perform the binary operation, first 3 then 6 or first 6 and then 3, I get the same answer. This is not such an important property as the first 4, but let us record this for the moment and then we will come back to it later. So, these are the properties of integers, addition on integers that I want to record, and I want you to remember that these properties, while they are so obvious for addition, they are not necessarily always true. For example, if you take multiplication on integers, there is no inverse for multiplication if you think about it, because if you multiply, what is inverse under operation of multiplication on integers? For example, 2 has inverse 1 by 2, which is not an integer. So, it is not clear that these properties always hold. So, with that, let us go to the second example, which again remember I am trying to give 3 examples to motivate the definition of a group. So, the second example that I want to give is the following. So, this is not so obvious, but I would like you to pay close attention to this. So, let us take this set consisting of 1, 2, 3. Okay. So, these are 3 elements. So, it is no less, I am not going to use any property of 1, 2, 3 other than that there are 3 different elements of a set. So, you all know what is a bijection of this set. So, I am going to consider bijections of 1, 2, 3. A quick recap of the definition of a bijection. What is a bijection? A bijection is a function from 1 to 3 to 1 to 3 which is 1 1 and onto. Okay, 1 1 and onto are properties of functions of sets. 1 1 means 2 different elements of the domain. So, this is the domain, this is the codomain, two different elements of the domain go to 2 different elements of codomain, that is 1 1. Onto means every element of the codomain is equal to an image of something from the domain. So, codomain is equal to the range of this function. So, for example, so I am going to use this notation to denote functions. Function 1 going to 1, 2 going to 2, 3 going to 3 is a bijection. Clearly, because 2 different elements, everything in the set 1 to 3 is in the image. So, it is a bijection. It is in fact the identity map. On the other hand, if you send 1 to 1, 2 to 1 and 3 to 2, this is not a bijection. Because 1 and 2 are different elements that both go to 1. So, it is not 1 1. Of course, also it is not on 2 because 3 is not in the image. So, I am not interested in functions which are not bijections. So, as I said, bijection is a 1 1 and onto map. Now, I am going to define a different set. So, define, which I will denote by S sub 3. S sub 3, the 3 refers to the fact that I have 3 elements in my starting set. So, S3 is the set of all bijections from 1 to 3 to 1 to 3. So, this is the set of all 1 1 and onto functions from this set to that set. So, this is my set now. So, I started with a set 1 to 3 consisting of 3 elements 1 to 3, and I have defined a new set now consisting of all bijections from 1 to 3 to itself. So, I would like to define an operation on S sub 3, but before that let me first list all the elements of S3. It is not very big. For example, the function that I defined earlier as an example of a bijection, 1 going to 1, 2 going to 2, 3 going to 3 is a bijection. Let us call that F1. So, what are the elements of S3? So, I am going to try to list all the elements of S3. So, the first function, because these are elements or functions, I am going to use F with a subscript to denote these elements. F1 is 1 going to 1, 2 going to 2, 3 going to 3. So, that is F1. This is in fact the identity function, meaning 1 goes to 1, 2 goes to 2, 3 goes to 3. What are other bijections? You can also send, let us call it F2, you can send 1 to 2 and 2 to 1, 3 to 3. Note that this is also a bijection, because different elements go to different elements, everything in the set is the image, 2, 1, 3 are all in the image. And if you think about it, what I have done is I have just interchanged 1 and 2 while keeping 3 fixed. 1 goes to 2, 2 goes to 1, but 3 goes to 3. Similarly, I can interchange 1 and 3. So, that means I send to 1 to 3, 3 to 1 and 2 to 2. Nothing happens to 2, but 1 goes to 3, 3 goes to 1. So, this I call F3. What are some other bijections? So, F3 is done. So, now F4, let us say I interchange 2 and 3. So, 1 goes to 2, 2 goes to 3, 3 goes to 2. So, here I do not move 1, but 2 goes to 3, 3 goes to 2, that is F4. Are there any other bijections? There are. For example, if you take if one of the elements is fixed, which is to say in this in F1, F2, 1, 2 and 3 are all fixed. In F2, 3 is fixed, F3, 2 is fixed, and in F4, 1 is fixed. If you think about it, if an element is fixed, if a function fixes either 1, 2 or 3, it must be F1, F2, F3 or F4. So, the remaining bijections, if there are any, must not fix anything. So, and there are such things. For example, 1 can go to 2, 2 can go to 3, 3 can go to 1. Neither 1 nor 2 nor 3 is fixed. So, everything changes. So, 1 goes to 2, 2 goes to 3, 3 goes to 1, and this is a bijection. Similarly, F6 also does not fix anything. It sends 1 to 3, 2 to 1 and 3 to 2. That is also a bijection, and some thinking on your part tells you that these are all the bijections. There are only 6 of them. So, S3 is the set consisting of F1, F2, F3, F4, F5 and F6. So, I am going to use these fixed specific definitions later. So, please note that F1, F2, F3, F4, F5, F6 are the ones I defined just now. So, F1 is the identity element, F2, F3, F4 fix exactly one element of the set 1, 2, 3, F5 and F6 do not fix anything. Now, remember that when we looked at the previous example of integers, the set was easier there, just the set of integers, but there we looked at addition. Here what do you want to look at? So, we want to get hold of an operation on this set. So, in other words, given two functions, we want to produce another function. There is an obvious candidate to do this. We have all learned in school, if you take two functions, we can compose them. In this case, because the domain and codomain are the same, we can always compose any two functions. So, consider the operation composition of functions on S3. If you think about it, if you take two bijective functions and you compose them, you get another bijective function. So, it must be again in S3. So, let us just work this out more concretely in a specific example. So, for example, if you do F2 circle F5. So, remember composition is usually denoted by circle, and in practice I will just omit the circle and write this as F2. When there is nothing, I will read it as F2 composed with F5. So, what does this do? Remember, I apply F5 first, then apply F2. F5, if you now see here, F5 sends 1 to 2, and F2, if you look at the previous page, F2 sends 2 to 1. So, F5, F2 composed with F5 sends 1 to 1, because F5 sends 1 to 2 and F2 sends 2 to 1. Similarly, you can just look at this, 2 goes to 3 under this and 3 goes to 2 under this. And remember, if you look back at the list of elements that we have listed in S3, this is nothing but this is same as F4. So, this is an example of what I mean by the operation being closed. So, if I take two functions F2 and F5 in S3, I compose them, I get another function of another element of S3. Now, let us do F5 composed with F2. Now, remember, I first apply F2 and then apply F5, and if you do this as before, you can quickly check that this sends 1 to 3, 2 to 2 and 3 to 1, and this is same as F3. If you recall, when I did the example of integers, I noted that after listing the 4 important properties, I said that integers also have a 5th property, namely the order in which I apply addition does not matter. When I add 3 to 5, I get 8, but when I add 5 to 3, I also get 8. And as this example suggests, as the new example suggests, order does matter here. If I do F2 composed with F5, I get F4, whereas if I do F5 composed with F2, I get F3. So, order in which I compose gives me different results. So, however, I can say that composition is a binary operation. So, I will say composition is a binary operation, which is same as saying, this is same as saying that S3 is closed See, note that I have not proved this, I have only checked that composition is closed at least for 2 elements. F2 composed with F5 is again in S3, F5 composed with F2 is also in S3. But here I am saying that if you take any 2 elements, compose them, I get another element of S3, and this is an exercise that you can do, and maybe later I will tell you how to do this if it is not clear, but this is an easy exercise, that if composition of two bijections is also a bijection. This is the exercise that will justify the statement that composition is a binary operation on S3, or that S3 is closed under a composition. Because if what is S3? Again, let us recall, S3 is the set of all bijections from the set 1, 2, 3 to itself. So, if you compose 2 elements of it, in other words, you compose 2 bijections, you get another bijection from 1 to 3 to 1 to 3. So, S3 is closed under composition. So, S3 with composition has the property that integers with addition have. So, this is the first property, remember. What is the second property? There is an identity. Again, recall in the first example, 0 is the identity element of Z under addition. Here, what is the identity element of S3? It is simply F1. Remember, F1 is the identity function from 1 to 3 to 1 to 3. So, for example, F2 composed with F1 is F2. Similarly, F3 composed with F1 is F3, and so on. This is clear because F1 is the identity element. So, composing with F1 does not change the function at all. So, there is an identity element. Now, the third property, interesting property, is there an inverse? Is there an inverse for every element of S3? There is. For example, if you do F1 composed with F1, which is often, for convenience of notation, denoted as F1 squared. What is F1 composed with F1? If you now go back and see, F1 sends 1 to 1, 2 to 2, sorry, actually I do not want to do F1 squared. F1 squared is simply F1, that is obvious. I want to do F2 squared. What does F2 squared do? 1 goes to 2, but 2 goes to 1. So, F2 squared sends 1 to 1, 2 goes to 1 under F2, but by repeating F2 we get 1 goes to 2. So, 2 goes to 2 under F2 squared, and 3 anyway does not move under F2. So, 3 goes to 3 under F2 squared also. So, what I want to do is F2 squared is F1. Similarly, if you quickly check, F3 squared as well as F4 squared is F1, which remember is the identity element from the previous page. Remember that F1 is the identity element, and in inverse is an element such that when you multiply, I use the word multiply here, but I should really use compose. If I compose F2 with F2, I get identity. If I compose F3 with F3, I get identity. If I compose F4 with F4, I get identity. What is an inverse for F5? If you go back to the definition of F5, you will see quickly, a simple calculation tells you that F5 composed with F6 is the identity element, because you have the definition of F5 and F6 here. 1 goes to 3 under F6, 3 goes to 1 under F5. So, under F6 F5 composed with F6, 1 goes to 1, similarly 2 goes to 2 and 3 goes to 3. So, F5 composed with F6 is F1. So, in other words, in words, F6 is the inverse of F1, F5, and also F6, F5 is the inverse of F6. So, every element has an inverse. And the fourth property is the composition of functions associative, which it is composition of functions is associative. This is something that you perhaps have done in the past. It is an easy check that if you compose two functions and then compose the third function is same as this. Okay. So, composition of functions is associative. So, that comes easily here. So, again the upshot here is S3, which was defined to be the set of bijections from S1 to 3 to 1 to 3, namely F1, F2, F3, F4, F5, F6, under the composition is closed. Under composition there is an identity element, every element has an inverse, and composition is associative. So, and I want to point out that the operation here is composition, it is not addition like in the case of integers. So, one more quick example I want to do, third example before we formally define groups. Third example, which is also one of the motivating examples for groups, is the following. So, consider an equilateral triangle. So, what is an equilateral triangle? So, this is a triangle with all three sides congruent. So, roughly it looks like this. So, I want to consider rotational symmetries of this. So, what do I mean by rotational symmetries? Rotational symmetries are the following. So, I want to rotate the plane on which this triangle lives, and a rotational symmetry 1 is one where after, if I perform a rotation, I get the triangle back. So, rotations happen around a point. So, let us say I rotate around the point in median point of this triangle. So, and rotation is always determined by an angle. So, if at home you can practice this by cutting out an equilateral triangle from a paper and just rotating it. So, if you rotate, let us call this side vertices A, B, C. If you rotate, what rotations preserve the triangle? So, this labeling is just for convenience, that is not part of the data of an equilateral triangle. If I rotate, what happens? So, for example, if I rotate by, so let us say I am rotating anti-clockwise. If I rotate by 90 degrees, you can quickly see I do not get the, so this is the starting point, this is the starting triangle. If I rotate by 90 degrees, I get something like this, roughly something like this. So, C will move here, A will move here, B will move here. This is not same as, clearly this is not same as, not same 90-degree rotation. Okay, so this is actually, yeah, this is not a symmetry. So, I do not want to spend a lot of time on what are the rotations which preserve the triangle, but the following happens. So, if you rotate by 120 degrees or rotate by 240 degrees, of course, you can also rotate by 360 degrees, which means we are not doing anything. These are the rotational symmetries of an equilateral triangle. So, let us denote these by some names. So, for example, I call this R1, I call this R2, I call this R3, and let us take the group or the set G to be R1, R2, R3. I am doing this example so that you get an idea of different kinds of groups that we encounter in mathematics. So, this is a set, and this set is simply the set of all rotational symmetries of an equilateral triangle. And as the previous two examples already indicated, we need an operation on this set. What is operation? Operation is again composition. So, operation is again composition. So, I can compose two rotations, and if you think about it, if you compose two rotations, you get another rotation. In this case, it is very simple. If you rotate first by R2 and then by R3, if you first rotate by 120 degrees and then by 240 degrees, remember I usually do not write the composition symbol, first rotate by 120 degrees, then by 240 degrees, cumulatively I am doing a rotation by 360 degrees. So, I get R1. Similarly, if I do composed by 240 degrees sorry 120 degrees, then again by 120 degrees, then I am composing by 240 degrees. So, I get R 3. Similarly, R 3 composed with R 3, if I compose by rotate by 240 degrees, then by 240 degrees I am rotating by 480 degrees, which is rotation by 120 degrees. So, it is R 2. So, as you can list all the possible binary operations. So, composition is a binary operation on G. So, the first property is true. Second property is that there is an identity namely R 1. Remember, R 1 is the rotation by 360 degrees or 0 degrees. Performing it does not do anything. So, R 2 composed with R 1 is R 2, R 3 composed with R 1 is R 1, R 3. Every element G has an inverse, as the previous page shows. R 3 composed with R 2 is R 1. So, R 3 is the inverse of R 2 and R 2 is the inverse of R 1, and as again as before, composition is associative. Just like the second example, composition is associative, composition of functions is always associative. So, that comes here for free. So, again just like the examples 1 and 2, the third example also we have a set G on which composition is a binary operation, there is an identity element, every element has an inverse and composition is associative. Okay. So, these three examples I hope give you some motivation to study groups, and I will stop my first video now. In the second video we will formally define groups and look at more examples.